Okay, I think we're ready to go. Welcome to the second lecture of the OLLI course, Energy, it should be Energy, Environment, and Economics, a Biophysical Approach. And I'm Charles Hall, and let's go. This presentation will talk about the early, well, actually not just the Earth, but uh, the early environment of the universe, such as we can tell. Um, and somebody asked about this last time, so here we go. The evolution of life and what it has meant, the particular role of the sun as our most direct energy source, resetting the evolutionary clock, the importance of green plants, adaptations forced on life in an increasingly oxygenated environment. What I think is a beautiful term, the ecological theater and the evolutionary play, and the evolution of increasing biotic complexity. And I'm going to give some personal uh, stories from my own teaching about how we actually measure these things in nature, with lots of pictures. So, a brief history of our universe here, that somewhere around 11, I think it's 11 billion years ago, we have no idea, nothing, or there must have been something, but there was something called the Big Bang. And we think it's got to be true because all of the galaxies are moving away from each other, moving away from some central point. And if you take their trajectories and move them back in time, some 11 or whatever it was billion years, they all come to a point, the same point. And so it seems like, boom, now, if that's how God works, then that's fine with me, because I certainly have no scientific clue as to how this happened. But when this happened, stuff expanded enormously, and the we had all kinds of protons and neutrons and electrons that began to come together as atoms, first of very light elements, and hydrogen and helium, which are very simple atoms, and then into increasingly complex atoms, um, like we have here on my coffee cup, lithium, beryllium, and the ones we're familiar with, carbon, nitrogen, oxygen, fluorine, and so forth. And all of these, neon, and all of these elements over time kind of stuck together and became bigger and heavier elements. And this took place over, I don't know, hundreds to thousands to millions of years of the galaxy. And then somewhere, let's see, here it is, 13.82 billion years ago is when they calculate this Big Bang happened. And where did all this stuff come from? They took the largest telescope on Earth and pointed it at a place in the sky where they found nothing, no galaxies. And then they aimed the Hubble telescope, the one that's orbiting the Earth, this beautiful, great big telescope up there, at this hole where there was nothing, and they found billions of galaxies. And so the universe is so huge, and we're just one little, our sun is just one little average medium grade star in the Milky Way, which is one, and that is just one of billions of solar or star systems in the Milky Way galaxy, which is just one of many, many, many billions of galaxies out there, and it's incomprehensible. And this time scale is also incomprehensible. You go to the Grand Canyon and you've got more than a mile of layers of rocks, of which, human existence is some tiny part of an inch. Um, and here we are, to my knowledge, but who knows, the only critters, the only entities in all of this enormous time and space who can understand to some degree what's going on. And I'm gonna talk about how hard it was to figure out what was going on. And to me, it's a fascinating journey of science. So, some 4 billion years ago, and this is probably 2 billion years ago or something, the Earth was a very inhospitable place. If we were on this planet, we would die instantly because there's no oxygen, and all kinds of poisonous, foul gases and so forth. Lots of magma activity and all kinds of who knows, and various solar system debris coming in. So you'd probably see a lot of meteors and a lot of it hitting the Earth and accumulating the stuff of the continents or of the seafloor of whatever. And also, this is debatable, but it probably the water came from somewhere else and smashed into the Earth. Who knows? But some very intelligent people are
I
taking
got some
some.
new shirts from my theater.
Oh,
And
lovey.
and
Just shit.
Well, somebody was going to eat it.
somebody please turn off their microphone and raise your hand if you want to ask a question with the electronic one. Um, Probably the Earth was smashed into by a Mars-sized blob that threw out the moon. That's what they think when they get the moon rocks. Okay, so the early Earth environment was anaerobic, that means no oxygen, very poisonous, and probably had mostly reduced elements, carbon monoxide, hydrogen, nitrogen, ammonia, and so forth. Carbon dioxide content of 70% or more compared to less than 1% of 1% today. Very, very different. Now, the three main sources of energy for Earth are one, radioactive decay that runs the sun, and it runs the heat coming out of the middle of the Earth that makes the magma. Geophysical, meaning tides and gravitational and also rain falling on the rocks and eroding and so forth. And of course, the sun. And we're going to talk about the sun. And here we are with 70% of the Earth's surface covered with water and water vapor, lots of it in the atmosphere, making it a very hospitable place for life because life as we know it requires water. And it's pretty hard to figure out how you'd make a living system without water. And so I drew this diagram many, 50 years ago, and it's a kind of an hourglass. And what's happening is this is the free energy, meaning energy that can do work of the universe. It's coming from the sun, which is gradually burning itself out, using up its hydrogen to make helium and helium to make hydrogen with fusion, to make however the sun works, and putting out photons. Photons are just units of energy that come flying out of the sun. And at this little hourglass, which is the Earth, which intercepts some of this massive amount of energy coming out of the sun, intercepts just a tiny bit of it, life has made devices for capturing that energy and running what you see here, the machinery of life. It's just an astonishing thing. And in so doing, taking this energy, storing it for just a little while or longer with fossil fuels, and then then degrading that energy eventually to low temperature gradient energy, low temperature heat, unavailable for work. So we say the universe is running down. It's going to take a long, long time. You don't have to worry about it. And in that process, energy that can do work is degraded to energy that cannot do work. And life has intervened in this process, and we'll talk about that. Now, the main factors that have affected the solar energy budget here on Earth, what we call the photon flux density. And you want to know what the photon flux density is? Go out in your backyard on a sunny day at noon and hold your hand pointing at the sun, your fingers pointing at the sun. And then slowly turn your wrist so your hand is 90 degrees to the sun. And what you're doing is increasing the photon flux density, the density of photons that are striking a square centimeter of your earth and of your hand, and you'll feel warmer. And then as you angle it away, you can feel your hand cool down. What you're doing is you're changing the energy photon flux density, hitting your hand, and this will have a great deal of help in understanding how the process of the Earth as a giant heat engine is working. So the things that affect how much sunlight any area on the Earth gets are what are called celestial mechanics, how the Earth and the sun are related, Milankovitch cycles, continental drift, and CO2. So you get a lot of talk in the media today about CO2, but it's just one, not even a particularly important one in the long range of things, determinant of our climate, temperature, and how much sunlight we get. Now, they asked a bunch of Harvard graduates, how come it was warmer in Cambridge, Massachusetts in the summer? And not one of them answered correctly. And the answer is because the Earth is tilted on its axis. I've learned this just recently. If you go and find Orion in the sky, and here's Orion, and you look about one Orion's width away, it should be on this side. It's to my right when I look from Ashland. Is the plane of the planets of the solar system. There was one time a while ago where all 7 planets were lined up in a line that was next to Orion, like that. So that's the plane. I just learned that. I thought that was pretty interesting. But anyway, in the summer, you see the axis is pointed at the sun, in December, it's pointed in the northern hemisphere, it's pointed away. But I used to spend as much time as I could teaching in Argentina in the summer, in their summer, which is December, January, uh, because the weather was good and the trout were biting. So the if you're wealthy or you have somebody who pays for your plane fare, as I did, you can miss winter if you don't like it. And I was living then in cold upstate New York. You can go to Argentina, the southern hemisphere, in our winter and be perfectly warm around the year. Now, at this time of the year, a little bit earlier than this, is what's called the equinox, which means the day and night are equal. And we have that in March and in September. This also means that in our growing season, we have 16 or 17 hours of sunlight compared to only 7 or 8 hours of darkness. And this is why we actually get much higher yields of crops in temperate zones than in tropical zones, because in the tropical zones, the nights are always about half of 24 hours. And during the nights, the plants have to feed themselves. And so in the tropics, you only get 1 or possibly 2 tons per hectare of maize, of corn, where we can get up to 10 in Iowa. I don't know what it is for Oregon in the northern hemisphere during our growing season. So that's allowed. Actually, agriculture is much more successful where you have long daylight, and even Manitoba and Saskatchewan, relatively north in those areas, have terrific corn yields. Okay, now the ancients tried to understand the movements, these movements here, of the earth around the sun, because it was really important to them to determine when the sun was coming back to England. This is in England, built by people hundreds of years ago, Stonehenge it's called, and there are a number of them. And it's actually an observatory, so that when the sun shines in certain ways through the rocks, you can watch December 21st, that you can watch the sun turn around and start coming back relative to your position on the earth. And it also helps you figure out when to plant, because you can't tell that simply by temperatures, as we've seen this spring in Ashland. You have to know when is the right time of the sun's progression to do your planting. In Mexico, the Pyramid of the Sun and the Pyramid of the Moon are giant solar observatories. And there's a guy from my undergraduate institution named Davini, who is an astroarchaeologist who looks at all these old structures and understands how they worked, how they were used by the priestly class to get information that allowed them to plan when to plant and when to do, and for different crops, and when to do this and when to do that, and how the gods were operating and so forth and so on. And the Aztecs had very, very complex calendars, apparently far more complex and intellectually interesting than anything that Europe had at the time. But the conquistadors tended to destroy them all because they were, anti-Christian or something, but for reasons the having to do with Christian principles. This enormously rich understanding of things that is written in a very difficult for us to understand language was destroyed by the conquistadors. And here's a joke. best of I can decipher it, it says we're all going over some kind of a cliff. So, that just as appropriate today, I suppose, as back then. Um, Now, let's look at a bit more is what affects how much sunlight and warmth the location on the Earth gets. So here's the sun, and I'm not going to get into how the sun works because basically I don't know, but it does generate photon flux and it has storms. And when it has more storms, we get more photons, but these seem to be relatively small changes over time. As far as we know, and the sun will supposedly expand and engulf us in 4 billion years, but don't worry about it. You're not going to live that long. And then we'll shrink, and who knows, becomes dark matter or whatever happens. So, first of all, in the history of the Earth, remember I told you that we think a big hunk of the Earth went flying into space and made the moon. And that left this large continental area. And this is where the continents used to be. Now, I remember in the 7th grade with maps of the world saying, my gosh, South America looks like it fits right into Africa. And I don't know how many of you thought about that, but I sure did. Well, this is what it looked like at one time. And if you see my maroon Prius, it's got a sticker on the bumper and it says Reunite Gondwanaland. And Gondwanaland was at one point this conglomeration. It's meant to be a joke. It sounds like a political statement, but it's obviously impossible to reunite Gondwanaland. Or, well, maybe if you're God, you can. I don't know. But this is there started something like this, and India went sailing right across the equator. So just amazing stuff. And I think that maybe what happened was the moon went out and the continents are redistributing themselves around, under the rotation of the Earth. That's generating, in some sense, increasingly a more distributed continental mass. But I'm not an expert about that, I can tell you that. Now, how do we know? I knew about this as an undergraduate because you would find some of these fossils, the same species or genus anyway, of the same critters in all these different continents. And I've seen this myself with Notophagus, the southern beach. So here I'm down in this part of Argentina, and it's got, I think, 7 species of what are called southern beach. And none of the species that we're familiar with, but you also find them in South Africa. And I don't know why they have it here in Australia and New Zealand. This genus Notophagus. And so I was very interested in that. And we understood that long before we understood the mechanisms and how it happened. This guy, Alfred Wegener, back in 1900, from the fossils alone, said these must have been connected in the past because the trees can't get across the Atlantic Ocean now or the Pacific Ocean. Now, we found the mechanism in the 1950s, and a bunch of geologists at Princeton came up with this abhorrent idea. Everybody poo-pooed it and said they couldn't be right because there was no energy source to move the continents apart. But then they found it. And it's an upwelling of mantle material into the middle of the Pacific Ocean and even Iceland, welling up and spreading. So that out here are older rocks, and right here are brand new rocks, and there are vents there with critters that are living on reduced sulfur coming out of the middle of the earth, and just amazing. And it's happening all around the world. Here's the Atlantic Rift, and there are plates here, and they're spreading out in the middle of the Pacific, and California is made by hunks of land that went crashing into the old North American continent. And yes, Mark.
Going back to the seafloor spreading zone
Yeah.
down the middle of the Atlantic mostly. Yeah. Something that I was totally fascinated by that I learned a few years ago is that the ecosystem that has evolved around those vents where the geothermal water coming up is our first discovery of life that doesn't depend on the sun.
That's
It's
not
just like
true.
it's
That's not
pardon?
true. That's commonly thought, but those organisms, and Cindy, I'm trying to remember, I used to know her when I worked at Woods Hole, was the first biologist to study this, and she thought that too. But uh, those organisms are dependent upon oxygen as a terminal electron acceptor, and the oxygen exists in the bottom of the sea only because of photosynthesis at the surface.
Okay.
Isn't
I'd
that
like to look
interesting?
into that. I'm not familiar with that.
No, hardly anybody is. But
Yeah.
just because I used to work with the people who studied that, I happen to have some inside information.
Yeah. I can see that from the biology point of view, but from the energetics point of view,
Well,
the
it's a
sulfur,
source of energy. That's true.
yeah, that's why I thought about it for
Yeah,
this class
and
because
as I said last time, you need a gradient
yeah,
between the reduced material. The hydrogen sulfide is reduced because it's got
yes,
hydrogen, and then it's changed to sulfur dioxide, and the electron loses its energy in that process and
yes.
runs the life.
So in this environment, though, the energy is derived from the heat and the sulfur fixing bacteria and is not directly dependent on photosynthesis, unlike our terrestrial
Hopefully
ecosystem,
oxygen.
I think. So.
Okay.
You're right, Mark.
Um,
Charlie, just a little interjection that those kind of environments are where one of the most recently discovered kingdom, which is the Archeans, are found in those much more less friendly environments. The extreme
well, they're less friendly to us, but they're friendly
not
to
friendly
them.
to us, but they can live in extreme environments that
Yeah.
other
We'll
kingdoms
get
can't
into that, John.
occupy.
Hang on. Okay, so you've got the magma that's coming up from the interior of the Earth, and it's pushing the lithosphere, meaning rock sphere, apart. And that's how that's the energy sources, the radioactive decay that generates hot magma in the middle of the Earth. So here are some maps as from different times, 150 million years ago. Somewhere between this graph and this graph is when oil was formed. So a lot of the oil that we produce is generated at when the Earth looked very different from where it is now. So that's why there's a lot of oil in the deserts of Saudi Arabia and so forth. Okay, now this guy, Milankovitch, forgot his first name, but anyway, Milotov or something, Milankovitch, who was Serbian and very proud of that, came up with, well, you've watched a top spinning, a child's top, and as it slows down, it starts to wobble. And the scientific name for wobble is precession. And there are three components to this precession. The can't read that precession. Oh, precession, obliquity, and eccentricity. So at some point, the North Star will be a different star because the axis of the Earth will change from our present North Pole to some other place. That takes place on a cycle of 26,000 years. The Earth wobbles, gets to a larger and smaller obliqueness relative to its plane of going around the sun at 41,000 year intervals. And at 100,000 year intervals, it becomes more and less eccentric. In other words, the planets don't go around the sun in circles, they go around in ellipses, and it gets more and less eccentric. So you put them all together and you get Milankovich's curve, and supposedly that determines the ice ages and so forth. I'm not quite convinced it's that simple, but okay. A lot of people work very hard at trying to understand these cycles. And then CO2, you can get past records of CO2 by drilling deep into the ice of Greenland, and you can get paleo temperatures, paleo meaning old. I mean, you get the CO2 directly out of the ice. You take a big long core of ice and slice it up, and you're going back in time as you go down in the core, and you get the oxygen out and look at the ratios of these isotopes, which is an index of temperature, and you see that the CO2 and the temperatures, paleo temperatures, certainly seem to be correlated in time. That's 800,000 years ago, and then this is recently. And here's the recent increase in CO2. So it certainly looks like CO2 is driving our climate. But there are some times when the temperature seems to change before the CO2. So what's the driver? What's the cart and what's the horse? Some argue that when it got warmer, the soils cooked and CO2 was released. That's a possibility too. So CO2 looks pretty important, but we don't quite know how it works. And just to tell you a fact, the most important greenhouse gas is not CO2, it's water vapor, which is 4 or 5 times more potent in total effect than CO2. And you don't hear people talking about that a lot. So I feel we don't fully understand these things. But I do think CO2 is something to worry about. Now, if you go back not quite 1 million years, 800,000 years, here's today's CO2, and today the jump from industrial fuel burning looks very big. This is within the geological times, though. And here's today's CO2. See that 1 million years is only this much right here. If you go back and look at paleo CO2 levels, as best we can estimate, there are lots of times it was much higher than it is today. Even including areas when there were lots of dinosaurs, lots of life. Oh, that wasn't meant to happen, but so I'm not terribly worried about the increase of CO2. It might be very bad for civilization, but I think life has seen it much higher CO2 in the past and will adjust accordingly. That's a very controversial statement. So this was meant to be a joke. I was going to take it out, but anyway, that's That's a bad joke. Now that we've achieved net zero, what do we do now? It's a bunch of cave. That means future cavemen sitting around. Now, about 4 billion years ago, something truly big happened, which was life. How did life originated? Okay, we have hypothesis number one, and this is natural selection and Charles Darwin and so forth and so on. And here's hypothesis two, divine intervention. And this is a tongue-in-cheek view of divine intervention by my favorite cartoonist, who's Gary Larson. And I'm a biologist, and of course, I think Darwin was the most amazing scientific mind there ever has been. And if there exists variation within a population of organisms, that a population meaning creatures, plants, or animals that interact with each other, interbreed with each other, and if this variation is to at least some degree heritable, and I would ask my freshmen to look around and ask if you look more like your parents than other people's parents, and they'd answer yes. And if there is differential survival and or reproduction among these variations, natural selection must occur. If these three things are true, and it's clear that they're true, natural selection must occur. Darwin came up with the idea of natural system while he was reading Thomas Malthus for pleasure one evening. And Malthus talked about the human population increasing exponentially and the sustenance, the food, increasing linearly, leading inevitably to humans having not enough food. That didn't quite happen. It sort of happened. We'll talk about that in a later lecture. Okay, these are the earliest signs of life we know, some kind of microbes that are found in these rocks in Australia. And then 2.4 billion years ago, photosynthetic cyanobacteria, that's blue-green algae, evolved, and they could use the sun's energy to generate energy-rich reduced compounds from water and carbon dioxide. Plants take water through photosynthesis and pull the two elements apart. So you have carbon and oxygen, and then they take, they do that to water, and they do that with carbon dioxide. And they put the hydrogen from the water onto the carbon from the carbon dioxide and make sugar. C6O6, C6H12O6. And that's sugar. And that's just an amazing thing. And what you could do then is store it and have a gradient of energy-rich sugar and oxygen and recombine them and use that energy to run life. And that's what you and me do. It's just an amazing thing. But it happened, and the waste product was oxygen. Oxygen is a waste product. And here's blue-green algae, something like that. You can see it. It's usually not a good thing from human perspective because it's toxic to animals. Now, you can see what difference it made. Here's a rock I got from Glacier National Park. And it's the same material below and above, but this rock, this shale, has iron in it. And the rock below, it's the same basic material, but here the iron is rusted. And here I can't remember, one's ferric and one's ferrous. And what happened is the atmosphere became oxygenated and all the iron started to rust. And the life that existed at the time, and there was lots of life, was adapted to a oxygen-free environment, an anaerobic environment. And when the oxygen came out, it was a toxic material. And life evolved probably by taking flagellate organisms and put them inside their cells as mitochondria. That's a whole marvelous story. And started using this waste material, oxygen, to make a bigger gradient between the sugars and the end products. And that allowed life to be much more powerful. And those organisms, including you and me, were the ones that evolved and became dominant on the planet, at least from our perspective, they're dominant. If you're a microbe, you might think something differently. Okay, the Cambrian explosion, all of a sudden, in the Cambrian 800,000 years ago, 800 million years ago, there started to be all kinds of critters like trilobites who've been on the earth 200, or were on the earth, they're not here now, 250 times as long as humans. And ammonites, these are animals that swam in the water, and as they grew bigger, they made their houses go out and so forth and so on. And this is what perhaps the old Cambrian Sea looked like. All kinds of weird critters, nothing like what we have now. But the same basic body structures were developed then. These are like the arthropods of today. Many of them were put down the basic body plans of all the phylum of today. The Devonian was the age of fishes. And an amazing thing happened when I was a kid. Was a fisheries biologist was in the fisheries market in South Africa and came across this critter in the fish stall, waiting to be sold. I don't know how they tasted, but this is what's called a lobe fin, probably somewhat similar to creatures that first crawled out of the water onto the land. This guy was supposed to be dead for more than 100 million years. And there he was. And so the fisheries biologists bought this critter and took it home and gave the fishmonger a lot of money for it and said, you find any other ones and you sell them to me. And they compared them. They had fossils of this critter, and they had rebuilt what the critter looked like from the fossils, and they had done an almost perfect job. In other words, we learned that our recreations of a fossil were pretty good. But here he was. There's no reason for him to go extinct. And down in the bottom of the sea, they're deep water creatures, and that was just amazing. Now, this guy, I think, is really an amazing guy, William Smith. He was the one who figured out how all of this stuff worked. Now, he was low-born. His father was a farmer, but he was very, very clever, and he made a living digging canals, because it was the age of canals. Here's one of his old canals, and making railroad grades. And so he chopped through a lot of rocks while doing this. And as he did, he began to notice that different rocks had characteristic fossils, ones that were only found in those layers. So here's fossils from 3 different rock layers in England. So he realized that they were from different times and that they had evolved differently over times, and many had gone extinct but had left others in their time, in their way, in the rocks. And so he made this first map. I think I like this one better, a little better color, of England, with London over here somewhere. And you see all the colors, but what's really amazing of his rocks, these are older rocks over here. And as you go across England, the rocks get younger and younger. And he's got this little diagram here, which I've blown up here. And you see, these are the old rocks, and these are younger rocks that were laid on top of them. And then at some point, they were all tilted. And so he could begin to understand that the rocks in England weren't random. They had been originally laid down on top of each other, like you see in the Grand Canyon, and then tilted, and was able to, he's called the father of geology, although Hutton and Lyell might be also considered fathers of geology, but then he laid it all down. And we begin to understand the earth. Now, and then he built a museum towards the end of his life. He went broke making these maps. He had them colored by hand, and he was so proud of them, but it cost him so much money that he went into debtor's prison. Finally, he got a job running this museum in the north of England, where he did something like this. So you could, I'm not quite sure why it's a spiral, but so you can see life going through time and time and time and time. Here's the age of dinosaurs. Here's where the coal was laid down in Pennsylvania and Mississippi and 100 billion years ago, more or less here, when most of the oil was formed, and up to modern times here. And here we are. He's got agriculture and a few other things. And humans are just a little tiny bit of this story. Now, occasionally the clock was reset. Big volcanoes or asteroids. And you've probably heard about an asteroid at the time of the dinosaurs crashing into the Yucatan of Mexico and throwing up an enormous cloud of dust that blocked out the sun, perhaps for years, and causing the air to become toxic, and all the dinosaurs went extinct, boom, in a period of days or hours. And maybe mammals survived because a few of them had burrows in the ground. We don't quite know, but here we are. And for all of you, I really recommend this book. It's a hell of a read. It's just a lot of fun. Dinosaurs at the Dinner Party, and it's $20, that's all. And people found these enormous footprints, just bigger than a person, back in 1820 or so. And they found these gigantic leg bones, much bigger than anything we had, and they had no clue what they were. And they had no idea of a world any different from theirs, because the Bible said it had been formed 8,000 years ago. And this is a story about how a bunch of non-professionals, citizen scientists, unraveled how the earth had changed, how the earth was different. And I just recommend it as a really good time read for all of you. And then in the 1860s, they found this fossil in a limestone quarry in Germany. And you see, it's got teeth. So it's a dinosaur, but it's obviously got feathers. And that's when we first understood that birds evolved from dinosaurs. So we are surrounded by dinosaurs. All the birds you see are dinosaurs. And dinosaurs themselves probably had feathers. So, these increasing discoveries, allowed us to piece together all this whole story of life. And this is sort of time from bottom going up. And of course, we put humans at the top. Well, we're not at the top because there are all kinds of microbes that can live only on us or in us. So they have to have evolved after humans evolved. But anyway, here we are, quite amazing. And here we are. And so here's another of my favorite cartoons is, well, you can read it. Just think Earth was a cloud of dust 4.5 billion years ago, 3 billion years ago, first bacteria, then sea life, dinosaurs, birds, mammals, and finally 1 million years ago, humans. Now in 1988, there's me, the acme of evolution. Well, that's obviously quite debatable to his friend, who thinks tigers are vastly superior to humans. Okay. Now, we're going to get into ecology for a bit. I'm probably going to run over just a little bit today. The sun shines on the equator. Now, remember, this is when I told you to hold your hand up to the sun. The photon flux density is greatest at the equator, although this moves north and south summer to winter. But let's just take the middle of the year. And this is in the air masses rise from the green vegetation in the Amazon and the Congo basin, warming up the air. And so they lift, and as they lift, it gets cooler, and the cool air can hold less water, so it rains on the equator. When do you need to take your umbrella to a tropical vacation? Tropical, incidentally, means between 23.5 north and 23.5 south, where the sun is directly overhead part of the year. You take your umbrella when the sun is directly overhead, because that's when it rains. This moves north and south with the seasons. And so it rains on the equator, and the air masses descend at about 30 degrees north and south. These are called Hadley cells, after George Hadley, who figured this out with respect to English navigation in the 1700s, which is very important. We'll talk about that later. And there are also more complicated things. The next cell is a Ferrel cell. Sorry for the crappy quality. And all of these form the main winds on the surface of the Earth. But here you can see the main winds are the westerlies, and you get up where the Ferrel cell is operating, and that's why our wind comes principally from the west, because of these big giant cells of the heat engines. And if you're down in Argentina and you're wading upstream fishing, you got constant 40 or 50 mile an hour wind in your face. It's much stronger in the southern hemisphere. Whoops, I'm not sure why I have. Oh, just to show you that where the cells descend, you have the great deserts of the world, 30 degrees north and south. And it's true in Arizona, true in Australia. And it's a lot wetter on the equator because they have rain every month of the year, principally. And that, Mark, you're going to have to wait. And that allows us to find the biomes. Biomes are big areas of common vegetation and animals. So here's a tropical rainforest. Here are desert adapted organisms with lots of spines to protect the water. Here's a savanna, which is somewhere in between, maybe 20 degrees north and south, where you get seasonal rains. This is in Kenya. That's Mount Kenya with a glacier on the top. It's right on the equator, but it's so cool it's got a glacier on the top, or at least I hope it still does. And that supplies water down to these savannas. Savanna is grasslands with trees. And then we get up to the Taiga, which is north. I missed the temperate zone, sorry, with deciduous trees. And here's the Taiga with pointed trees to shake off the snow so it doesn't get too loaded by snow as we go to Canada and Russia and Norway and so forth. And I think I got time to do this. We're going to start talking a little bit about ecology, and I'm an ecologist, and so of course I like to talk about energy and ecology and the historical development of the trophic concept. Trophic means food energy. So this guy Tansley came up with the idea of an ecosystem that we could think about all the organisms in a given patch of land together. And this is my academic grandfather, Evelyn Hutchison. And he started everyone thinking about how to go and measure things in ecosystems. And this guy started the energy transformation idea, Raymond Lindemann, and he thought of in ecosystems as trophic levels. The first trophic level is the plants that capture their energy from the sun, then herbivores that ate plants, and then carnivores that ate the herbivores, and then top carnivores that ate anything they wanted below them. And he estimated from this pond, Cedar Bog Lake in Minnesota, he estimated that there's only about 10% of the energy went from one level to the next. And that's why it's a lot more efficient to feed humans generally from plants than animals. Because if you take the food energy and you feed it to a pig or a fish or whatever, then at least you get only 10% of the food than if you ate the plants directly. But of course, humans don't like to eat grass, so it's a little more complicated. He called his approach the trophic dynamic or food changing approach to ecology. And I'm very much from that tradition. And I guess I've said most of these kinds of things. So I'm going to show you, this is my advisor, Howard Odom, and he came up with a lot of very interesting ideas about how to think about this. Anybody wants, send me an email, and I'll send you a recent paper talking about maximum power principle, one of his most important ideas. Okay, and he came up with a series of very innovative and clever ways to quantify and represent the energy use of an ecosystem. Now, I'm going to show you how we measure it. One way is just to look at how much for annual plants, just go in with a square meter grid and chop out every month of the year the height of the grass. In this case, this is Spartina grass, ocean saltwater grass. And we just go and we chop the plants every month, and the accumulation over the year would be the net production. Some of it would be eaten by animals. Or you can measure the gas changes. The plants, when they photosynthesize, they give off oxygen and they take up CO2. And we have machines for measuring each of those. So we can look at the rates that happens, and this express it per 10 square centimeters or whatever, and then we blow it up to entire ecosystems. Here's a means I invented for sampling fish. How much fish is there in a square meter of the bottom of this estuary? And you would be amazed to come out with a garbage pail full of fish from one sample like this. This is where I did my postdoctoral work on Long Island. And now I'm going to show you very quickly how I used to do it for many, many years in my class in systems ecology. Systems ecology is about learning how to represent an ecosystem or other system in a computer. And most people start with the math, and I start with taking my students out for a 3-day weekend in the field on this beautiful little creek, Little Sandy Creek, and just some pictures of it. Just, I love environments like this, probably because I like to fish for trout in them. And and a large part of the energy that runs this system, most of it comes from little algae or diatoms on the rocks, gives them their kind of golden hue, but some falls in from leaves from the surrounding ecosystem. So we can measure those. So we go out and we camp, usually about 30, 35 students. We camp for the weekend. We have a professional cook. We have all kinds of equipment set up out here. We set it up like a military campaign. So this is General Hall, that's me, that's directing the whole thing. And then we have various lieutenants. I remember Omar, he was the fish lieutenant because he went on to become a good fish biologist and so forth. So all of these are people that have different things they're in charge of. I give what's called a soliloquy. That's ESF, Environmental Science and Forestry, where I used to be teaching. And I give them an hour-long talk about what it is they're doing. I teach them how to measure oxygen in the water with what's called a Winkler, and then show them how to do the chemistry. The changes in oxygen will tell you the change in the energy used or produced by the plants and animals. My wife took my class. There she's measuring the flow rate of the water by following a lemon for an hour. And I almost ended our marriage. I'll tell you, don't have your. But anyway, we both survived, and she, in a way, was my best student ever. And here's a couple of ladies, or people anyway, that are measuring the dimensions of the ecosystem, the width, and then every tenth of a meter across, they measure the depth. And they do it at 2 kilometers of stream. And it was just lovely. When the weather was good, it was just lovely. And this is a lady from France who was getting her PhD in our program, and she's measuring a Winkler from the water itself. And this is a woman from China who's doing the titration to do the exact amount of oxygen in the water. And it's all set up with a little bit of beer to see you through the night. And these are a bunch of Winklers that he's getting ready to titrate, if you know any chemistry, and went on day and night over 2.5 days. And then here's somebody else who's studying all the insects that they capture. So we organized it as 6 different teams. So we had, Lieutenant Chemistry, Lieutenant Physical, Lieutenant Bugs or Insects, Lieutenant Fish, and so forth. And we had benthic chambers, which would take a piece of the ecosystem and enclose them in a box. And then you'd measure the oxygen changes over time during the day and during the night. You can see the kind of golden look of the algae. Oh, I love this. And then here's another fellow doing another benthic stuff. I don't think anybody ever taught ecology like this. Boy, this was a great hole for fish. We'd always get a big trout from under the bridge there. That would be, everybody'd be very exciting. This is a stonefly, one of the kinds of insects that were there. And here are a couple of ladies that are measuring, getting, I guess they're taking their sample out here, and they have a device, I don't have a picture here, for sampling how many insects there are per tenth of a square meter of the stream. Here we block off a section of stream, and you see they're measuring trout here, getting the weight and the length. There's a lot of work to do this, let me tell you. And this lady here is running the fish shocker. You put the electricity in the water and the fish turn over, and you can get everyone that's in this blocked off with 2 nets set of water. And this is Jerry, my long-term TA, who was so good at this. He is now running the entire water supply for New York City. He's in charge. I mean, he's just a kid from the Catskills, but boy, was he good in math. So here's a typical bunch of fish, trout, and suckers and so forth, a few minnows. Wonderful. And then we write it up. We actually published all this. Anybody want to see it, I'll send it to you. Made a flow diagram of the energy going from the sun through how much photosynthesis there was and how much of that went to all of the different parts of the ecosystem. Oh, and we also did it for tropical forests, using a slingshot to get to the top of the trees, going up with tree climbing devices. This was for Nancy's PhD thesis. She was amazing. And testing the maximum power hypothesis. Oh, where's the picture of, that's a Lycor analyzer of CO2 exchange and of the leaves. And she did this going up to the tops of the trees. We get up there, we shoot a piece of string up with a great big slingshot, and then get this climbing rope over the top of the tree, and up Nancy would go. And she did this for years to do her PhD. Beautiful PhD. I had such great students in the day. And we tested the maximum power hypothesis and found support for it. Okay, let's stop there. I don't want. That's enough for today. Let's have some questions. Woo! Just let me get out of this share screening thing. Stop share. All right, so there's an introduction to how you measure these things. And I'll tell you, it's a lot of wonderful work. Now, everybody turn your microphone off unless you're making noise, and raise your hand either right there. Mark has his hand up. Go ahead, Mark.
Yeah, going back quite a number of slides when you were talking about the global weather patterns.
Yeah.
And you had a map of the westerlies come over in North America. I noticed that over the Atlantic, they illustrated hurricanes, and they have the direction of the wind going in a clockwise progression. And then in the South Atlantic or Indian Ocean,
Well,
it was
that's a little bit
cyclones, and
different.
they were
Those
going
aren't
in the opposite
hurricanes.
direction.
Those,
counterclockwise.
if you go on the Weather Channel, not what's the Weather Channel I use for the 10-day in Wonder Map on the not the Weather Channel. What the hell is the weather? Just a second, I got to find out.
Well, I just have a very simple question.
Yeah. Those are not hurricanes. Those are just the winds here going in one direction, the winds here going in another.
Oh.
And these are the big spirals you see in the Wonder Map off of our coast. They're not hurricanes. Hurricanes are little intense ones.
Well, that was labeled as hurricane. And the reason I'm asking is because it had a similar kind of cyclonic flow counterclockwise in the southern hemisphere. And I had always thought that hurricanes and cyclones were interchangeable term. But according to that, hurricanes rotate clockwise in northern hemisphere and cyclones counterclockwise in southern hemisphere. So they actually are a little different that way. I thought they were synonymous.
Let me look. I am at a loss.
Sounds like
I
sounds
might
like
be very
toilets flush
wrong.
differently in the
Yes.
northern and the southern
Right,
hemisphere.
right. It's exactly the same thing, but I had always just said, oh, cyclones is just another word for hurricane and vice versa. But that may not be the case. Oh, you don't have to go way back. Oh gosh.
Well, here we are.
There.
Hurricanes exist there, but these are not by themselves hurricanes. They're massive systems, circular systems, and you'll
Yes.
see them off the coast. You see them circling like that off the coast of Oregon. I see them almost daily when I go to my weather, looking at my weather. Um, my wonder map. I have a weather system. I can't think of the name of it, and I'll email it to you for crying out loud, where you can see this every day.
Okay.
Okay. So, but these are giant circular systems, and they shouldn't have been labeled hurricanes. It's where hurricanes exist. Now, do these big systems contribute to hurricanes, which are much smaller? I
Yeah.
don't know.
I was just
Yeah.
I was just comparing the hurricanes as labeled to cyclones in the southern hemisphere, going in the opposite direction. Thank
Well,
you.
I'm interested in the problem, Mark. If you
There's
send
no
me an
problem.
email,
I
although
understand now.
I have yours, because I'm interested in hurricanes as non-living systems that operate to extract energy from the ocean. They
Hmm.
build structure that pulls the heat out of the ocean that makes them bigger and stronger. That's a very interesting concept. Okay, Meg.
Two things. The first one is the Aztec calendar is divided into 26,000 year cycles. Just thought, since you mentioned,
Really?
yeah,
That's the same as a Milankovitch cycle, isn't it?
yes, exactly. And also, but I wanted to understand more where you were talking about CO2 and its effect on like global warming and climate change, but you said that the hydraulic system had a much greater effect. Could you go into that a little bit more, please?
Uh, Only in one statement that if you look at the models, the IPCC models of the effect of CO2, they recognize that the CO2 isn't the main greenhouse gas. The Earth would not be getting very much warmer, a little warmer, from the CO2 alone. In the IPCC models, the CO2 causes warming that causes more water vapor to be stored in the atmosphere. And in the models, the water vapor does the heavy lifting of the warming, does the major part of the warming. I think it's something that needs much more public exposure and discussion, because it's possible. I'm not an expert on this, but I used to do a lot of work on carbon. It's possible that the warming we seem to be observing is not due to CO2, but is due to an increased albedo of the Earth, decreased albedo of the Earth, so that with less ice cover, more energy is being absorbed. Now, both of them would get you into some funny positive feedbacks. I don't think we really understand the climate system as well as a lot of people would have you believe. Now, that does not mean I don't think we should restrict CO2. I think that's a good idea. But I'm worried that science is taking too hard a position on CO2, and that in time, the importance of these other factors are going to be more broadly used and used by, pardon me, the wrong types against science.
Well, then would you say that CO2, the hockey stick graph and how, CO2 has really gone up in the atmosphere in the last 200 years since industrialization? So,
No question about that.
yeah, you're saying that, but you're saying that there are these other factors that need to be incorporated. Would
Yes.
that be correct? Mhm.
Yeah. Oh, no question the CO2 is increasing. But as I showed you in my pictures, there are times in the past when the CO2 was much more.
Mhm.
And we had dinosaurs in Alaska. And how did the dinosaurs make it through the long winter nights in Alaska?
Mhm.
Life is very adaptable,
Mhm.
not necessarily our lives. Okay?
Okay, thank you.
I like your questions. Oh, David, what a fine name you have. Please turn on your microphone.
Thanks, Charles. Hey, one quick question, just a clarification. When you said that water was introduced to the Earth, was that in your mind or known to be at around the time that the
Hello?
moon was formed?
At
Hello.
the time the what was formed?
The moon was formed? When was water introduced to the Earth?
I think from before the time the moon was thrown out, if it was thrown out, which I guess it was, and after that too. I think it accumulated over a very long time period.
Okay. So
But I would say, let me give you an absolute ridiculous precision. Between 4 and 2 billion years ago,
okay.
it rained a lot from space.
All right. Thank you.
Please don't quote me on that. Stella? Yeah, microphone.
Short question. You might refer to it later, but could you break down the percent of sources of energy? You said there's radioactivity, there is geophysical, and there is solar. And I suspect solar is a major in terms of bio
Well,
availability.
it's all nuclear in a sense. No, the sun is nuclear in a sense.
Right,
The heat in the earth is so, in a certain sense, both of those are nuclear.
right,
And gravitational, you think of geophysical tides. I grew up on the ocean, so tides were a big thing. And that, but we don't even hardly know how gravity works. Um, Newton came up with this beautiful equation that predicts the attraction between two bodies, and it's exact. We can shoot a spaceship to the moon using only Newton's laws, and there was not even a need for a mid-course correction. But Newton's law of universal gravitation is only a description, and a lot of people, I've been reading on this recently, a lot of people didn't accept it because the idea of a force acting at a distance made no sense to people who understand F equals ma. They didn't understand how a force could operate at a distance. Now, Einstein came along with the idea of curved space-time as the origin of gravity. Does that account for tides? I guess so. How does it account for tides? You got me. So that's in what's bigger, geophysical or nuclear? Well, nuclear in all those galaxies, and except if you think about it, wait a minute, I'm going to correct myself. You look at all those galaxies, that's only things that emit light. But 80% of the stuff out there is dark matter. You can't see it, it doesn't emit light. And so, but it has gravity. That's how you know it's
Hello?
there. So that geophysical gravity
Hello?
is in a sense as large or larger. I don't know.
Okay, how are you?
Um,
There's
okay,
Anthony, who is not muted. And
Anthony, do you have a question? Meg has another question.
I'm
so
74, but I'm very interested, but I need a special plan. My name is Mickey Mouse. I'm a mouse. Do your plans cover mice?
What's happening?
I
Okay,
think
well, I've got money. You got a special funeral for a mouse. You know who Mickey Mouse is? Mickey Mouse, Donald Duck,
Anthony needs
Walt
to
Disney.
mute.
I think you have the ability to mute everyone if you want to, and then people can unmute.
But I think in general, I want people to be open and verbal.
So,
Okay, Meg, you're on.
so my question is just to get a visual of the moon being flung out, was the Earth already spherical? Was it, how did this, it sounds like from the description it was like there was already
Well,
sort
I
of a
mean,
solid-
matter, I mean, space, dust, some people say, glommed together by gravity, if they were close enough.
They were close enough.
Yeah, I mean, this is Newton's law of universal gravitation, which is a superb descriptor, but not a superb mechanism.
Mhm.
And so all the stuff that was close enough glommed together, and we know that space stuff tends to glom together into a circle or a globe. Now, that's almost like Newton's law of universal gravitation. I can't tell you why it's a globe. I guess it's some optimal district, or Earth is slightly pear-shaped, but it's a globe. And the moon is a globe. And Jupiter is a gas planet, but it's a globe. All the 8 or 9, whatever it is, planets are globe shaped. So that's some kind of optimal way of gravity putting together stuff into globes, whether it's liquid like Venus, or I guess, or Earth, or gaseous like Jupiter or Saturn.
So part of the globe was flung out and that destabilized it. And then the movement of the planets is trying, or not planets, but
yes. You had it.
Okay, good.
And the movement of the continents are trying to reestablish this circular equilibrium on a spinning globe. So I suppose you could take a drill and put a glob of clay on it and take out now remember, it was hit by something and that threw out a bunch of stuff that then accumulated into the moon, is the theory. And if you spun this glob of clay on a top of a hand drill, would it reconstitute a globe? I think it would, if you did it just right.
And this is just something I read last week about the association of major earthquakes with sunspot activity the day before. And they were throwing out, and I'm just saying this to you because it's so fascinating, that it depended, that increased proton density, and in major faults, which generates these electrical charges, and in major faults, it can set off a major fault that's ready to pop immediately. So it was just kind of blows my mind that
I don't understand how that would work though. So
it's something to do with the electrical charge, but it wouldn't be for, it would depend on where the proton density, I guess, was focused or something. But anyway, I'm just throwing that out. That was a new thing that I read.
where did you read it?
God knows where I read stuff. No.
Okay. That doesn't work too well for me. but if you find that article again, send it to me and I'll give you a more thoughtful response.
Thank you.
Diana, unmute, and if you are not shy, turn on your camera. Hi.
Challenge today. You answered hello. You answered some of it in her question. It was back to the moon and do they know where the chunk came from? Is there any evidence of the impact where it split some of the continents and where that was at?
I think we would have called it an asteroid today, I think. And the Earth has been hit by pretty big asteroids, but rarely. I mean, once in a while over its history. And the one we know the most about is this one in Yucatan. And, you know, they find the crater and you can actually see a circular image of, what do they call them? Centrals or something.
Cenotes?
My dog. You can find you can find evidence of the impact in the water bodies of Yucatan. I mean, there's all kinds of stuff in Yucatan. There's in huge cities that we had no idea about because it was covered with jungle vegetation. And they start clearing them and there was, you know, vastly larger cities than existed in Europe at the time. So all kinds of stuff that we barely know about. So anyway,
so no evidence of that, but there is evidence that the rock on the moon is
where it hit.
Or what chunk flew out.
Yeah.
What chunk, where is that chunk missing?
Well, I mean, we have no idea what the I mean, right now there's a lot, you know, millions apparently of asteroids, and we see them as shooting stars, and they're just little specks of dust that make shooting stars or golf ball size things. And occasionally I read something about one about as big as, I guess a golf ball to a hard ball, somewhere in there, came crashing through somebody's, I guess they just came crashing into their driveway and plowed into their driveway and left a crater. And so, and the place to look is Australia because it's not covered with vegetation.
Right.
And it's actually pretty much pockmarked over the 4.5 billion years or whatever that the Australia as a chunk of real estate has been somewhere on the planet. I have no evidence of what this chunk was. I've not read anything, but I'm just not aware of it.
I just thought maybe that's how they came up with the theory that the moon was actually composed of debris from the Earth or some chunk of the Earth.
Well, I thought it was green cheese.
Yeah.
I'd like to take this moment here to ask if anybody is dissatisfied with how we're going about this. Are we doing? You have any feedback for me, Karen? I can't hear you. You're.
I have to say, I'm extremely pleased. I have no complaints whatsoever. Bringing up and putting together all kinds of fascinating details about giving three-dimensional background for the world we are living in and trying to keep livable today.
Well, I think a lot of it had to do with my particular training by Howard Odum. And if anybody wants any more on that, I have a marvelous interview of my years as a graduate student that I guess I would really like somebody anybody have experience with setting up websites? I'd like a website for this course, and I'd like one, actually like to pay somebody to set one up for me personally. John, what does that mean?
I don't have any expertise, but I do know, for example, our chorale director, Rogue Valley chorale director, has a Google site where he posts all sorts of things and links and documents and everything we
Well,
need.
could you ask him how he made it come to be?
Well, it's Jaron Jorgensen. He's the head of the choral music at SOU. If you want to try to reach him, I don't know. You probably make a direct contact would be the best, I think, for someone like that. But I think a lot of people use this Google Google Doc, I think they call it, as a way to connect with groups of people over the internet.
Well, I sure want to get to who was the person. I sure want to get the person who missed the first lecture, and I can't. I'm trying to work with Eric, who's, I guess he's gone now, but oh, he's still there. He's very skilled at this kind of thing. So, but I'm willing to pay somebody to try to put this together a little bit, and I'd like anybody who's interested in my education with Howard Odom, send me an email, and I'll send you some things that are really a lot of fun. I think you can see I've had a lot of fun being an ecologist.
Way
And
too much fun.
would you say way too much?
Way too much fun. I do have another point just on the globe thing, Charles, about the. I mean, the cell would be a globe too if it weren't for the cell skeleton poking various parts out, and microtubules, microfilaments, all that can change the shape of the cell. But if you get rid of those, the cell just rounds up like the moon. So it must be some free energy thing.
I think I've read about that sometime in my past, but I wouldn't know. You can find anything with Google. I'm just amazed. You say, why are planets round? I bet you could put that into Google and get all kinds of good answers.
Yeah. Before we end, I'd like to just I have a quick comment about the process.
Excuse me, who are you?
I'm Linda. I have
Linda.
my
Hi, Linda. Okay.
Hi.
Turn on your camera if you want. If you don't, that's fine.
Okay. Let's see.
I like to interact with people.
All right. Here we are. Let's see.
But it's not
Here we
required
are.
if you don't want. Okay.
I got it. So, I like to read and have a few minutes to understand the slides. So, and sometimes I miss stuff and I'd like to be able to go back.
Yeah, no. So Eric, I hope, we did it last year with Eric. We're going to try to put all the slides on a site. Both the lectures and the slides on a site.
Okay. I noticed that
there's doing that now. I think
Okay,
I got to pay for some kind of file transfer system, so because they're too big to go on regular pathways.
Okay, well, yeah, if you could just perhaps just slow down a couple seconds, that would be very helpful for me.
Slow down?
Slow down a couple seconds, not a lot, just a little bit.
I had a recommendation. I know what you're saying. I like to read it too, and the slides go by fast, but he's talking, so he keeps up with that. His speed. I take screenshots and I post it into a Word document. That's how I capture. So you might.
That's a good idea.
Second,
like
it works for me.
Yeah, because I can look at it later.
I'm very, very happy to take a question on email. chall@esf.edu. I mean, you get that every time I send out the announcement anyway.
Okay.
And yes. And I went a little bit fast today because I added a bunch more stuff.
Well, it's very
I mean, did
enjoyable.
you like the stuff
It's
about
just-
the Smith and the coelacanth and stuff? That's all new.
Oh,
I
Well, I'll just
found,
take
you know,
pictures.
Smith, who
That'll,
did the map
that'll
of
look
England,
good for me.
fascinating. And if you're looking for something good to do, go buy dinosaurs at the dinner party. That's such fun.
I like your figures, Charlie. I think I'm doing screen captures of a number of your figures too, because you found some good ones.
Well, let me see if through Eric I can make the stuff available to you. But who is it that missed the first lecture? If you want to get it for sure, come by my house, 2532 Old Mill, off of Tolman Creek. And
With the thumb drive?
come by and we'll have a beer on my porch. I don't care. Okay. Anything else?
I have a quick question.
Yes.
Let's see.
Is this Jeannie?
Yeah.
Hi.
This is sort of probably a stupid question, maybe. When you showed the graphic of the movement of the continental bodies, the dissolution of the mega continent, are illustrations like that are so interesting with the undersea structures? Is that a computer module, or is there some way that we actually can see what's under the ocean?
Oh, I used to work at Woods Hole, which is an oceanographic place.
Yeah.
And mostly they see to the surface with sonar. How long it takes for sound to go down and then bounce back.
Huh?
And you know, you can do that to very tiny amounts and get so those very detailed descriptions of the bottom of the ocean are true things.
Wow.
And but underneath, you know, they go down with robot submarines, or occasionally, I got to show you, there's a submarine called the Alvin that goes way, 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 way deep. And they go down and they stick thermometers into the rifts and into the cracks where the stuff's coming out. And I used to know just barely some of the people that did that. I mean, it's just amazing stuff that they do. But how you have a different kind of sonar that's more difficult, different wavelengths or whatever, that lets you see below the surface. And so you can see the structure of the asthenosphere and the continental material and whatever and the magma shows up. You can get a view of that inside the earth.
Wow.
And so you can do that. And you can also go up to Iceland where it's that kind of stuff is how Iceland came to be. That's why there are hot springs in Iceland, so that they heat all the roads of Reykjavik have in the sidewalks have pipes under them, and they've got free hot water. So and there's a place called the Blue Hole where you can go swimming in the middle of the winter in Iceland. So that's a place where the Mid-Atlantic ridge comes up to the ocean.
That's a mind-blowing
I'd
thing.
love to give a lecture on oceanography. I used to teach oceanography. I loved it.
Wow. Thank you.
Okay. Okay, you saying bye, John? Okay, bye, John. Bye, everybody.